So here we have the full picture of this dot map that's put together predominantly the lower 48 states. We can scroll over here and we see a little bit of Alaska and we see some Hawaii over there. So we can take a look at the whole 50 states there. As we were talking about, this is data that's provided from the latest census. There's color encoding for each person in the United States based on their background. So we might zoom in. Before we were talking about Texas, so we might zoom in here. And as we get closer in, so first we'll look at Dallas-Fort Worth. And we can see particular patterns here. We have, quite a blend here in Dallas of different backgrounds. So one of the things that stands out is we have a fairly significant population, folks who are defined in the census as Hispanic, Black. We have different parts of the city with strong Asian populations. We have regions that have white populations in them. And you can see some of those patterns, some aggregations, but we also see, as we get closer in, we see a lot more detail. So the picture certainly looks different. Say, for example, when we focus in on a particular area and we get up close, we see that there's all kinds of folks from different backgrounds that may live in particular neighborhoods. And so we get a little bit different picture depending on what scale of the map we're looking at. So as we back out, we see a little bit different picture, a little bit different pattern. We can also tell that, yes, this is in fact an urban area, and these are more rural areas out here just by the collection of people. We see these are smaller towns that have collections of folks and quite a lot of land that's out there without very many people. Now, in aggregate, kind of the same way, if we get quite a ways out, we can also see population throughout the United States, and we can very clearly see a pattern of density in the United States. Essentially, that this half of the United States is much more dense than most of the other half. This is quite a bit of rural area, mountainous and rural area. We also see there's quite a bit of density here on the West Coast. And there's a really good reason for this particular pattern, that a great deal of the immigration flowed through the eastern United States. Over time, it moved westward, but there's also sort of a slowing effect where folks tended to stay or not move very far from the place that they had immigrated to. We also see that density. There's Ellis Island is here, significant immigration center of the United States, particularly when immigration was predominantly by travel from ships. There's also Angel Island here in the western part of the United States near San Francisco that served as a huge immigration hub for the western part of the United States, that we see a lot of density and population here as well. We can see kind of the same way when we're looking at an overview, we see particular patterns. We see the significant influence of Hispanic populations here in the South, as well as Black or African American populations here in the South. And while a fairly dark part of the country's history, the same type immigration pattern that we saw here, a lot of folks with African American descent, the South was their point of immigration into the United States, often in a forced way. So we can see some of those patterns when we're zoomed out in an overview. When we zoom back in, we can take a look at different areas. So we'll take a look at Miami here that we were looking at previously. We can take a look at the different populations that are located along the Florida coast here, the southern tip of Miami, that has different backgrounds. And we can also see quite a bit of density where we see the color encoding strongest. It's that way because of our 1 dot equals 1 person, and it's encoding a whole lot of people. And let's see if we add some map labels here. So we see New York there, Philadelphia. We zoom out and we see some of the immigration and migration patterns throughout the country. We can also see some of the major cities like Denver, Salt Lake City are starting to collect larger populations, but we still have a great deal of the United States that has much smaller populations. And so we might see some particular clusters here. Here, we're taking a look at some collections of Native Americans. Ogallala is a particular Indian tribe. Native American tribes have quite a bit of influence in the Dakotas, in this part of the country, that we find, and as well a number of locations all throughout the West, including Oklahoma. So hopefully this gives you guys a sense of how we can utilize what's called a dot map to map different kinds of data and overlay that, in this case, in a geographic map. And just for fun, before we finish up here, let's head out and take a vacation in Hawaii and just kind of see what that looks like. We can see the Hawaiian Islands there. Honolulu is the major island. If I remember correctly, Hilo's an island. I think all of these were formed from volcanic activity. We can see a lot more detail on these islands where folks live when we zoom in. We see an airport there. A couple airports there as well. So okay, So hopefully that gives you guys a sense of sort of overviews, how you can have one view when we drill down, get closer in. The picture might look much different. So now we'll take a look at some mapping performed by the website CityData. I encourage you guys, particularly if you're working on a visualization project and you need some data, some information from a city or a municipality, to check out CityData. Here we're taking a look at a couple maps from the CityData website for Dallas, Texas. And the way that the encoding, the data encoding works here, so we see sort of the outline of Dallas itself, the outline of the city of Dallas. And then we have two different data sets encoded here. So the first one on the left, we've encoded age. So basically the population based on a different area of the city, different neighborhoods in the city. And the way that the encoding works is basically on a shading of sort of very light to dark purple. And so what we see here, if we take a look at age, so we see quite a bit of folks that are a little bit older in these parts of the city. We also see that some in the south, some in downtown or to the east of downtown. And then on the east side here, sort of a mid-range, and then some other areas of the city much younger. Now, one of the things that we might want to focus on as we look at the map to the right is how a couple of these factors, demographic factors, may overlap. So here we'll take a look at income. So this is annual income encoded the same way. And so we see a significant mapping of high income folks in the north part of town, basically in North Dallas. And if you look, you can see quite a bit of overlap between these two, where if we put those two factors together, it becomes clear that at least in Dallas, these two factors are present together, where you have a number of folks of advanced age that are also fairly high income. Now, it's not universal, because we've got some other areas where folks are in advanced ages, but it doesn't necessarily cross over with income. Now, a couple things that might be interesting to note. So in previous elections, prior to George W. Bush becoming president, can you guess which neighborhood he might have lived in? So if you'd guessed in North Dallas, you would be correct. And these two factors provide what you might think of as the ideal voting pattern if you're running for office. Folks of advanced age always vote. They also have the ability to make political contributions. After leaving office, George W. Bush also moved back to the same neighborhood. It also happens to be the same neighborhood that most mayors of Dallas, at least for the last 30 or 40 years, have lived in or do live in. So even though it's just encoding two simple factors, you can actually find out quite a bit coding just a couple of factors. Now let's take a look at another example of using a dot map. This one happens to be looking at global population density. And I want you to take a look at it for a couple minutes and study it, and then we're going to come back and talk about what you may be seeing. And ask yourself a couple of these questions. Where in the world is it more dense? Where is it less dense? How is color used there? How is the size of circles used there to illustrate what's going on with the population? So we might start in the conversation we had before. We had discussed that there's quite a bit of density in this part of the United States, we can see a sort of a comparison of the circles up here, that these light blue circles are sort of a medium density. We see the yellow and orange circles, particularly in these high population areas, as a lot more population dense. And then we can also see where we have our large circles. If you recall that our population was not nearly as dense in this part of the country, but it was dense over here on the West Coast. And we can look at other areas of the world. We might take a look at India, China. We see that's significantly encoded with our smaller yellow and orange dots. We see yellow and orange dots here in Europe. So we've got a number of locations that looks like some fairly dense population. And then we've also got some areas throughout the world that have a lot lower density population. And so this presents, this particular dot map presents the information and encodes the information a little bit different way than the dot map we were looking at, where one dot equaled one person, which was unique in its own way. Here, we're encoding different groups or densities of people with the different sizes of our dots that we're utilizing here. So now let's take a look at probably the most famous, or one of the most famous maps in history. This is the Beck map of the London Underground, developed by Henry Charles Beck. And this map is very unique in that it was constructed in a different way than what most geographic maps are constructed. Now, as we take a look at it, we can see some physical features of London. So here we see a river. I think this is the Thames. We see a number of different train lines. So these are all underground subway lines in London. We see that they're color-coded. Their stops are highlighted. We also have some encoding of the two different types of train stations. We have your regular train stations that has a dot, but we also have the open circle, or the open dot. Some folks might call it a donut, that encodes interchange stations. So anytime two subway lines have an interchange, we change the dot to define that. Now I want you to take a look at this and ask yourself who this map was designed for. So as many of you may have guessed, this map was specifically built to help those that ride the London Underground. And it is optimized toward the things that someone who rides the train cares about. Now, what does a person riding the train care most about? Where's the stop that I get on? And where's the stop that I get off? And how many stops are in between? And so this map does a wonderful job of optimizing to help the riders see the sequence of stations until they may exit the train. Now this is useful, this optimization is useful, and it helps riders basically use the train system. Now, a couple of things I want to highlight that this map is not designed for, it does not do. So this is not a geographic map. So geographic proximity of these stations to each other is not accurate. And you can pretty well tell this. You can tell on each one of these lines that stations are equally spaced out for ease of readability. They're not laid out in the exact proper spatial proximity or distance from each other. And that has been done intentionally to make it easy to use the map for train or subway riders. And this particular map is not designed to basically lay out the geographic proximity of the train stations, because the riders, that's not really their priority. That's not necessarily something that they would care about. They would just care about which stops they would cross, how many stops are in between the two stations that they cared about. Now, this map has also been emulated many, many times throughout history. We see a very modern interpretation of the Beck map here, the Seoul Metro map. And you'll notice it's encoded very much the same way. It places an emphasis on the sequence of different stations, the color of the particular line that a rider is riding on. We do see some geographic details. So we have the Honggang River here that passes through, and that helps us to provide sort of a certain landmark of which side of the river a particular station might be on. But again, this isn't necessarily a geographic map, and that's not what it's optimized for. Now we're going to take a look at probably one of the most famous usages of maps to solve a particular problem. So this is a historic map. It's often called the Snow map or the John Snow map. And what this map is a neighborhood map, a particular area in London that centers around Broad Street. And we might start looking at this map asking the question, what does it mean to see? So how do we see things? So here, this map was designed to help determine what the cause of cholera deaths were in a particular neighborhood. And I'll walk everyone through the encoding, the way that this map's built, so you guys can probably see the streets that run throughout the city. And then the unique part of this map is at the particular addresses where persons, individuals, had become ill with cholera and died, their person or their statistic is counted, and basically kind of a stack or a type of a bar chart is defined at that particular location based on the number of people that had died in that particular location from cholera. And so we will see there are some locations that have deaths from cholera. Some locations have quite a few. Other locations may not have as many. But what this does, once we've laid out our different areas, our deaths in different areas or different addresses on the map, is we can begin to analyze what might be going on or where the problem is coming from. So we can see that some locations have more deaths than others. This particular area is the most prominent, that stands out, is clearly probably having the most deaths of all the other areas. And we also see some locations that don't have any deaths. So on sort of deeper analysis, particularly driven by these stacks of folks that have passed away, as a cause for the cholera deaths was sought, it was ultimately determined that cholera was a waterborne disease. It was basically being spread by this particular water pump here on the corner of Broad Street. The first clue that the cause of death, what's causing many of these deaths, must be close to here just by the sheer magnitude of the deaths that are in this close proximity. So if you're trying to figure out, gosh, what's causing this, you'd probably start looking in this area. And this is what was found. And ultimately, the source of the cholera was determined that the outbreak began, there was an infant in this particular building, something to do with changing the diapers of the infant that had developed cholera, got into the water supply here, and then this pump basically functioned as a death pump for everyone that was within walking distance of getting water from this particular pump. You can see when it's a little bit outside of walking distance, we don't see near the desk. We have some here, but this was probably close enough walking distance. But when we get further out, we just don't see those desks. Another thing that's quite peculiar, you'll notice that this area is labeled as a brewery. And it's very interesting to see here on Broad Street, all the desks that developed close proximity, but in this building, basically, there were no deaths reported. And probably the logical explanation for this is the occupants, at least the workers here, were drinking beer instead of water, and that actually protected them from this particular waterborne disease. Now here's the same map, and you can see walking distances from the pump defined. So there's a particular walking distance, how long it takes you to walk, that helps to capture within a particular period of time how long it takes to walk from these different locations to that pump. Now we also have a modern technique called the Voronoi diagram, where when we have different encodings, or we have different data sets that are laid out on a map, this particular technique will find the center point of that area and assign it a zone. So here we see the same diagram, or the same map with the Voronoi diagram applied to it. We can see some of the separation there and see how this particular section or pane the map has drawn itself based on the data observations within the area. Now let's take a look at some data maps. So these maps were created by an acquaintance that I'd met at a conference. His name's Brian Wilt, down here at the bottom. He works at Jawbone. And this particular data visualization project was associated with their wristband monitoring product. And this is one of the spin-off benefits of that particular technology. Jawbone is now the owner of the world's largest sleep study database. The reason why they're an owner of the world's largest sleep study database is because the owners of the wristbands would wear these wristbands to bed. And so the inactivity or the shift in activity for the user of the wristband could be recorded, aggregated, and some of the results of that aggregation is what we see in front of us here. Now, this particular map is titled The Average Bedtime by U.S. County. So what's encoded here is different bedtimes, the time people go to bed by county. And that's determined, based on the, condition of inactivity being recorded in the data coming from the wristbands. So we'll see here, we've got, if it's a little bit sort of light gray, we might have an earlier bedtime, light blue, just a little bit later, medium blue, a little bit later, dark and very dark blue, on up into some of the darkest blue or black encoding, where folks go to bed much, much later. And so we can take a look at this map and study it a little bit and tell me what you see. See if you see anything peculiar or unusual or particular patterns in the map. So some of you guys may have noticed that in this particular part of the country, there's a lot more darker counties, noting that people go to bed much later. Now, there is a particular dynamic that's going on here I want to highlight to you guys that these are time zones in the United States. So this is Eastern, this is Central, Mountain, and Pacific time. We can see that encoding here, particularly in some of the major cities. We see that folks go to bed much, much later. We can also see that pattern here in the center, but I want to bring to your attention sort of this darker pattern that's to the right side of these timelines, particularly these two. It's a little bit here. But I want to ask you guys to think about what might be going on here. Why does this particular pattern exist? So, as some of you may have astutely figured out, that there's a change in the number on the clock. So, I may move from a county that's right here on the western side of the time zone. It may be a particular earlier time. We will say maybe it's 10:45. We might move to a county just to the right of the time zone, just to the east, and we see that the bedtime is much later. Now, sometimes folk sort of think, well, hang on, there's this whole sunrise, sunset phenomenon going on, and that's absolutely correct. But remember, the way that the sun and the earth interact together, the way that the earth rotates, folks in this area are all pretty much going to have the same amount of sunlight because they're pretty much on the same place on the earth. So that's not really the differential. But there is a differential here. And now let's take a look at what some of the insights from this data visualization are. So some of the things that we can see, cities like New York, Atlantic City, Miami, Las Vegas, and New Orleans stay up late. And this makes perfect sense, right? So New York City is a city that never sleeps. Atlantic City is a big gambling hub. It's common for folks to stay up late into the evening in Miami. In Las Vegas, folks are gambling all night, and it's quite common in New Orleans to stay up late as well. So this makes a lot of sense to us. We can say our New York, Atlantic City. We can go out and see Las Vegas. We can take a look at New Orleans. These locations in Miami, these locations all, of course, stay up late. Now, the first time I met Brian, he was trying to solve a particular puzzle that he had. He had found some dark areas that had much, much later bedtimes that weren't major cities. And he was trying to figure out what in the world is going on in these locations. And I brought to his attention, because two of them I had recognized, West Lafayette, Indiana, and College Station, Texas, were both the locations of Purdue University, Texas A&M. So these particular locations, Indiana University, Purdue University, Texas A&M, Penn State, and Ohio University all stay up late. In fact, at Texas A&M, for at least a quarter of the year during football season, there is a cultural event called Midnight Yell Practice, where the entire student body goes to the football stadium at midnight to cheer on the team. Now, this is sort of a peculiar behavior, and no doubt skewed a particular time frame for that location. Now, we can also see the western edges of a time zone retire earlier than the eastern edges. So we see that in a pattern. It's lighter on the western side of each of these time zones. And why is that occurring? Why do these folks retire earlier than folks just on the other side? And the phenomenon that's going on there. It's a behavioral phenomenon that the number on the clock influences behavior at the border of time zones. So if you happen to be in this particular time zone, here on the left-hand side, you might be have an earlier bedtime. If you're on the right-hand side, you might have a later bedtime. Now, in proximity to is the sun up or sun down, these are actually the same, almost the same measurements, or the perspective of whether it's light outside or not for folks in a county on each side of that time zone would have the same sort of experience with lightness and darkness. The difference maker is that folks on this side of the time zone, even with the same amount of light or lack of light, they will take a look at the clock and conclude, it may not be that late, where folks on this side of the time zone line look at the clock, it's an hour later, and say, oh man, I gotta go to bed. So that's part of what this phenomenon is here, with lighter on the eastern side and darker on the western side of these time zones. Now this is from the same person. Brian Wilt put this together, Jawbone, but this is a little bit different encoding. So this is total hours of night sleep by U.S. county. So what's being encoded in this map is how many hours of sleep folks get in different counties throughout the country. So here we can take a look at the encoding, and we see some things that we might expect. So folks in New York, Atlanta, Orlando, New Orleans, Houston, Dallas, St. Louis, Chicago, Denver, Las Vegas, Phoenix, Los Angeles, San Francisco, Seattle, they don't get as much sleep at night. So there's clearly something going on with people in major cities receiving less sleep. There's also a phenomenon with folks in rural areas get more sleep. We see that with some of the darker color encodings. Now I want you guys to think about this particular set of maps, both the blue one and the green one here, and see if you can figure out what might our bias be. What bias have we embedded or baked into these maps that we probably need to address with the footnote or communicate up front that this particular bias might exist. Think about how this data was collected. So this data was collected from folks wearing wristbands. So that may or may not be an accurate reflection of the overall population in that county. What it may be a reflection of is the individuals who are wearing a jawbone in that particular county, who may or may not be fully representative of the behavior in that particular county. So what we've done, when we encoded this map, we've included the particular measurement bias for the way that we collected the data. We're collecting it from folks' wrists. And perhaps one of the best ways to help contrast to see this bias is understand that we didn't collect any data from all the people who do not wear jawbone wristbands in particular counties in the United States. This map does not accurately represent all those folks that aren't wearing a jawbone wristband. So we should be careful in those situations not to overinterpret the results, but just speak to them clearly about what they actually say. So, sort of recapping, people in the major cities were found to receive less sleep. People in rural areas receive more sleep. The color coding in these maps represents the area versus the population. And this is a problem with all population-based area maps, that you may have collections or large clusters of folks that live in one part of a particular county. For example, it may be an urban area, and they all wear Jawbone wristbands. There may be 3/4 of the rest of the county where people either don't wear or have never heard of a Jawbone wristband. But when we go to encode a particular county, because we had representation of Jawbone wrist wearers there, we spread that encoding across the entire area of that county. Whether or not there are folks, with an equivalent measure of density wearing Jawbone wristbands evenly throughout the entire area. Another problem of bias that we have with this visualization is that participants of the measurements may be traveling or transient. And this is particularly true in the case of Las Vegas, where a large percentage of the measurements being taken in Las Vegas, very likely folks that do not live there. They may be traveling or transient. So that's another bias that we've baked in. And then just in general, this reporting bias of risk-based measurement that we've discussed. And it's sort of like this. It's you can easily overinterpret a set of results by saying, well, the people who wore these particular wristbands in that area, they all went to bed at a certain time or slept a certain number of hours. But that may not be representative of the whole group, just the folks that wore wristbands. And you might see a similar phenomenon, broadband internet access or internet access in general, that you always need to be careful in interpreting your results to guard against statements like, well, everyone has a wristband. Now let's take a look at some of these differences in how we shape maps and what it can do. So take a look at this particular map. So this is the map of the presidential election between Barack Obama and John McCain. And take a look at the encoding and tell me what you think it looks like. So many of you may have come to the conclusion that just based on the color encoding and the size of the area that's encoded on this particular map, that it was pretty much a tie. That we may have been surprised that John McCain didn't win the presidential election. However, when we look up at the electoral vote totals, it's basically a landslide. So Barack Obama picked up 365 electoral votes, which is a proxy for the population. And then John McCain picked up, roughly 50% that vote total. And so if we look at the two quantitative measures, it tells us one story. If we look at the state overview, it tells us a little bit different story. It may not tell us everything that we're trying to figure out here. Now we can also take a look at the same map by county leader, or by county at the county level. So here we still have the same electoral college votes up at the top, but we see quite a bit more variety, a very different picture than even what we saw at the state level. So when we add some detail here, it looks even more significantly like a whole country of red, that there were very few Obama voters But this, of course, was totally not the case. There were a very large supply of Obama voters. And what this is, what's going on here is there are a number of very large land areas or counties that are encoded as leaning McCain or voting Republican. However, the issue, the problem, this looks like it would be an easy McCain win, except it's not representative of the population. Lots of these areas that are defined in red don't have a lot of people there. And predominantly the major lever in federal presidential election or other significant elected office is getting individuals to vote, basically the populations to vote for you. And area representation or in an area map does not give us a full picture of anything other than, yes, it's true that that particular county leaned toward McCain. Now here's an insight of shift in the voting pattern. So this may be one of the most useful visualizations in this series, in that it tells us different counties in the country where people became more democratic. And it also captures on the sliding scale here where folks became more Republican. So we see a couple of patches here through this particular part of the country. Arkansas, we've got Tennessee in there, a number of other states. We see some down in Louisiana as well. Those counties became more Republican, where you see a lot of other places in the country became much more Democrat or leaned voting for a Democrat. So this gives you a sense of what's going on or what's changing, what's shifting in the country. Now, are any of these area maps an accurate representation of what has actually gone on in the election? And if you guys have been listening closely, of course, you know that might not be the case. We might say, no, it's not an accurate representation. And in the next visualization, it should help to illustrate why it is that folks say that. And what we can see here is we have different size bubbles based on the number of people that voted for a particular candidate. Yes, it's true if we look throughout the Midwest and the South, as well as a great deal of the West, we see that, yes, in fact, those are all encoded in red, but they don't have these colossus cities. You do see that LA, Seattle, Portland, San Francisco. So we see very, very large proportions or combinations of voters, populations of voters. And we can see the difference where this particular circle might have encoded Los Angeles County, Orange County, compared to one of these red dots that might have also encoded a county. But the difference is there's a whole lot of people in this county versus this one. And we see that pattern in a number of the major cities who voted for Barack Obama in this particular election. Now, the next visualization is basically an idea, it's sort of an artistic idea, to accurately present a data visualization of the area with the counties scaled by population. So this is, in fact, the U.S. map, And a couple things I'll point out to you. You might notice that this would be the equivalent of the Los Angeles population. So we see a very large population there. With the county scaled by the population instead of the square meters, square kilometers, square miles. When we do that, it gives us a fairly different picture, but a picture that's somewhat similar to this one, where we see those large population centers play an outsized role in area allocation in this type of map encoding. Now, in thinking about scaling other important variables, how do we put together, what's a good ratio, and how do we scale a particular variable? Well, these are all just conversation starters to get you thinking about how you might encode data in a particular way. So the first one is land area managed per capita. So here we see basically the point being made about population. But equivalently, someone that owned a very, very large ranch here in Texas could argue that all of their area for their ranch, and I think one sold to Stan Kroenke, who is the owner of the new Los Angeles Rams, that I think it was about 300 square miles, something like this, one ranch. And so Stan Kroenke basically owns his own county here in Texas, and might argue that if he voted a particular way, that the entire area that he manages, he would want color encoded in the way that he voted. So land area managed per capita is sort of the counter argument or the inverse argument to encoding how much population was in a particular area. Defining the gross domestic product by county. So we often have conversations about the gross domestic product of countries. We compare them. It's a sign of economic success. But drilling down at a deeper level, and a student team did this for their project, found the top 5 counties that contributed to GDP in the country. And so if you think about it, if you're coming up with a set of policies that created economic success, we might look to those particular counties that had the highest gross domestic product. We might want to look at number of businesses per county. That might be a meaningful way to encode variables. Where there are businesses, there are jobs. So that might be a useful starting point for a visualization. Property value per capita by county. So we may want to get some sense of how much is particular properties worth divided by all the people that lived in that county. And then finally, you could take it gross domestic product by charitable contributions. So gross domestic product is basically economic success, and then charitable contributions is giving back. So we might want to look at that as some sort of a ratio to see, well, what are the most generous counties in the United States? Okay. So in summary, map creation is a system of trade-offs on accuracy. So if we encode for population, we might be doing a disservice to area, and if we encode for area, we might be doing a disservice to the populations in particular areas. So there isn't any particular map that we can create or any data visualization that's not going to have some bias in it. That bias may not be intentional, but it may in fact be there, likely will. So we have to determine, make good design decisions on the trade-offs on accuracy. We will scale maps at an appropriate level for the content. So depending on what this is a map of, whether it's an apartment complex or whether it's a city, we want to scale the map to an appropriate level for what we have in the map. Insight representation should drive map construction. So we want to show something unique. Take a look at this. You're not going to believe this. That sort of perspective. And a good practice is to determine the insights, and then that should drive the map construction. And then finally, do some self-reflection and understand the bias that you're creating in a map. When you begin to create a map, think about, well, what am I biasing based on the particular design that I've created for the map. In every map, we're going to have bias, and the most successful map makers and data visualization folks decide to encode something on a map and then very thoughtfully figure out, well, what have I biased here? How is this particular map biased? And often that can be resolved just by putting a subtitle or a caption up front that you're noting the bias. You want those viewing the data visualization having that as information to help them be better informed about the content in a map.